So after Ben's very nice talk about optimal QAOA for the max K-cut problem, now we continue with Adam Glos talk on the same method for the traveling salesman problem. And it is actually a pleasure for me to introduce Adam Glos, a long-time collaborator of mine. So it's really good that you are here. And please, Adam, the stage is yours.
Thank you very much. It's actually a big pleasure for me to talk about, unfortunately, still not published results. We're still working on this. There's much more work than we expected behind this.
Soon.
Soon, yes, hopefully soon. Let me start us with a quick recap of what we knew so far thanks to the Ben's presentation. So our main focus will be QAOA. QAOA could be seen as a mixture of quantum annealing and variational quantum eigensolver, where we still have some ansatz, a sequence of quantum gates with some trainable parameters, but this ansatz from this variational quantum eigensolver was inspired by the adiabatic evolution. In the adiabatic evolution, we start in a ground state of some well-known Hamiltonian, very simple one, very simple to produce, and then with continuous time changing Hamiltonian, we are slowly bringing up the objective Hamiltonian, the Hamiltonian which describes our problem and for which the lowest energy state is at the same time the global optimum of our problems. We take this continuous time-dependent evolution, apply the trotterization, which in this context means that we interchangeably apply this simple Hamiltonian and objective Hamiltonian for some time. And if we have sufficiently many Hamiltonians applied with sufficiently small times, then we are promised that at the very end of this evolution, we will result in a ground state of the target problem of the objective Hamiltonian. In fact, in QAOA, in quantum approximate optimization algorithm, we hope that this ansatz can be beyond this, meaning that we are not really need to choose very small angles, but we can use external classical optimization procedure to optimize these times Pi and Ri so that we have some very good state. What is exactly the problem? The problem is that contrary to variational quantum eigensolver, to VQE, we need to actually encode the problem on the quantum circuit. This means that all these degrees of freedom, which defines instances of our problem, needs to be put to the quantum machine, which in general is costly. Now, again, another big question is how low can we go with it? So Ben already introduced all of the important quality measures. There is number of physical qubits, effective space size, which is defined as logarithm of the subspace of this linear space we are living in, number of gates, number of parameterized gates, depth on two architectures, whether qubits are connected all to all, or they are run online, and finally the energy span, which is the difference between maximum and minimum objective value. All of these have some very natural lower bound. For example, when we want to encode the problem or write the QWorld, a hobo, or any other representation, we should not expect that the number of qubits will be smaller than logarithm of the number of solutions. For example, for max K-cut, where we have k possible colorings for each node, we have k to the n number of solutions. This means that we need log of this number, which is n log k qubits at least. Similar argument is for effective space size. For number of gates, we kind of assume that there should be as many gates as there are degrees of freedoms. For example, for max K-cut, we have n squared edges, which basically its presence of absence of this edge is our degree of freedom. So if we have n squared number of edges, under assumption, each of this degree of freedom, each of this edge is contributing with one gate, we have the lower bound on number of gates around the number of degrees of freedom. It's a little bit less obvious what to do about the depth. In our case, we just take the following. If we can apply gates in parallel, like on the IBM machines, for example, and we know the minimum number of gates, and if we can reach minimum number of gates and qubits, then the minimum depth would be number of gates over number of solutions. This is not really perfect because the more qubits we would have, then actually you could bring this down. But if we optimize and minimizing number of qubits and gates, this is very good lower bound for depth. Finally, for energy span, well, ideally we could just compute the difference between maximum minimum objective value, but we usually don't know this value, so we are usually satisfied with some relatively tight upper bound on this difference. All of these quality measures have very significant impact on, first of all, possibility of running the QAOA on quantum computer, but also on the possibility of getting quantum advantage for the given problem. In particular, Bencher, who was presenting the previous presentation, focused on max KCAT, where we, in our future work, we propose an alternative QAOA ansatz, QAOA design, in which we reached all the optimal values. We dropped, essentially, we dropped the dependencies on the number of colors. You can see here the dependency on the color is basically logarithmic, which we believe that this, at least for some types of instances, sufficiently complicated ones, that this presentation would be dedicated for the future quantum machines, or current one, or maybe current are a little bit small. And the reason why you go with new approach with simulated QAOA is exactly as for this example, that when we try to encode the Hamiltonian, maybe of the binary problem, which is actually very simple to compute. Note that this is just minus and operation. Writing say Python script who would compute this value is like few minutes job. When you would try to encode this into quantum circuit, we would result in an implementation with exponential number of gates. This is something which is simply not possible for the current quantum machines. At the same time, we have extremely simple, which actually can be even improved more representation, where you have we have polynomial number of gates. Whether this is assumption is justified is questionable, but for sure it is just better. So what about summarization of the maybe still previous presentation? Was the result we obtained for the max KCAT interesting? I guess it's very strange slide for the middle of the presentation. So definitely it was interesting, and there are multiple reasons. We reached optimal quality measures, as I spoke before. We essentially dropped the dependency on K. This dependency is now very, very weak, almost could be ignored in most cases. Because of these two reasons, our representation, our ansatz fits perfectly for the noisy intermediate scale quantum era. And also, which is probably the most important thing, max KCAT is extremely important problem which has some real applications. So definitely and objectively we can say results for max KCAT were interesting. However, at the same time, we were not really satisfied with these results. The thing is that this improvement, while significant, lacks some fundamental breakthrough from our side. We basically took the full representation, reformulate this quantum circuit could be understood so that it more fits in this simulated variant, which was better. Initial state, we were simply expecting something more. And the solution for our lack of satisfaction was to move into more complicated, at the same time paradigmatic actually problem, which is traveling salesman problem. Traveling salesman problem can be defined as follows. We have a bunch of cities, so we know what is the cost of traveling between any pair of the cities, and we want to find the shortest, closest route, in the sense that we start at actually any city, we visit all the cities, and we go back. This problem is well known to be NP hard. Thus, it may be an interesting target problem for NISQ optimization. At the same time, this problem is relatively simple, sufficiently simple that we can provide lower bounds in the sense of this quality lower bound I talked before for all these quality measures. We have n factorial solutions. Then we need log of n factorial number of qubits. Same for effective size, which is n log n. We have n squared edges with attached wave, so we have n square gates at minimum. Def comes simply from dividing n squared over n log n, so it is something like n again. And the annealer span here, we need some assumption that the cost matrix consists of only bounded elements, say at most 10, for example. And in such a case, the annealer span is proportional to the number of cities. So let us focus first on the state-of-the-art representation of this problem, which was proposed in Lucas' paper, in his very, very famous paper. It was called, I think, Isaac model representation for NP problems. I also have a reference at the end. In this representation, in this encoding, we have something very similar as it was for max k-cut with one hot representation, meaning that we have n squared number of qubits. Each bit is actually bits maybe for now. Each bit is represented as a square, and black square means that we assign value 1 to this bit. If bit, say, in the second row, third column, has value 1, it means that it visits city 3 at time set 2. So, for example, at time 1, it starts in city 1, then goes to city 3, city 6, city 2, city 4, city 5, and we need to go back, so we go back to city 1. So let us investigate this a little bit. If we would see at any possible combination, first of all, note that we only allow one black square in each row and each column. This is important because we only allow that one city is visited at a given time. This is why we have one black square in a row, and each city is visited exactly once, which means that in each column there has to be exactly one black square, 1, 1. 1 bit equal to 1. But if you look at all possible combinations here, then you can see that between time 1 and time 2, we can have all possible combination of moving from one city to another. For example, we can go from 1 to 2, 1 to 3, 1 to 4, etc., 2 to 1, 2, 3, to 4, etc. All possible combination. What does it mean? When we would try to make a binary representation of this problem, we need to encode the whole cost matrix. Cost matrix is the matrix which defines the cost of moving between cities, between these two registers. What is worst about this fact is that we need to repeat this process for all pairs of consecutive registers. So between time 1, time 2, time 2, time 3, time 3, time 4, time 4, time 5, time 5, time 6, and finally, where I missed the curly bracket, between time 6 and time 1. Because of this, we artificially multiply numbers of degrees of freedom, because this cost matrix is repeated n times in this representation. Since constant matrix has n squared degrees of freedom, because there are that many pairs between cities, we repeat it n times, then we have n to the n cubed artificial degrees of freedom. Now, let me remind you, we assumed, we believe that is a realistic assumption, that the number of degrees of freedom is the lower bound for the realistic lower bound for the number of gates. Exactly because of these issues, many known representation couldn't go below this n to the cube number of gates. These are some further aspects. Because we have that many gates, we either have a lot of qubits or we have a very big depth of the circuit. For example, if we take something like, let's call it for now volume of the circuit, which is number of qubits times number of depth. For XQAOA, XYQAOA, we have n cubed. Similar for these two last variants of the QAOA. But for GM-QAOA, which is with the mixer called Grover mixer, it is even worse. It is just n to the 4. So actually, at least for some representation, this n cubed representation is fundamental. This lower bound on number of gates n cube we kind of motivate here is not working in general. For example, if we take the ILP integer linear programmer representation, it's called Miller-Tucker-Zemlin, if I remember names correctly. We don't have time to city representation. It's more like city to city. Because of this, if we have integer variables saying that go from this city to this city, then we don't have this redundancy. But there are other problems which also cause results in having n cubed number of gates. So unfortunately, this do not solve this issue. So what we have done with our SIM-QAOA, we start in the superposition of valid cities. So that's kind of in graph coloring case, meaning that for each time we already make sure in the initial state that only one square is black. We also choose Grover mixer. It is very convenient. It's particularly convenient for us because it guarantees that the amplitude moves only between feasible states, feasible solutions to us. And finally, we designed two pseudocodes which describes our problem. The first pseudocode verifies whether the current solution, current bit sequence is a permutation. And the second one simply implements the cost of the given route. Unfortunately, time is limited, so I can't go through all of through the details of how these pseudocodes were implemented. I can only briefly describe the idea as kind of similar how it's done in Grover search, meaning that we consider a quantum circuit which set up some extra ancilla qubit to 1 if the root is permutation and 0 otherwise. We rotate this ancilla qubit and then we uncomplete this quantum circuit. This is how it works for permutation. For the cost root, it's slightly more complicated. However, what is the result? The result is threefold, actually. First of all, we created a version of QAOA which is up to polylogarithmic factors better than all the one we presented before. According to our knowledge, this is better than all the existing ones. This is almost because, like, for example, for depth, there are there's XQAOA and XYQAOA which don't have this logarithmic factor. So this is something we don't have. Secondly, actually twofold, not threefold. Secondly, which is maybe even more interesting, is that our representation almost reaches the optimal values we derived before. For example, you can see that the number of qubits, energy span, number of gates, it all matches with the optimal derivation. Depth is slightly longer than we should have. Unfortunately, this comes from the fact that we need to deal with kind of integer numbers. So understanding some registers takes some time. I believe that this is the actual lower bound. It's not possible to be beaten. First aspect is that we somehow correlated to what to other factors, is that we were able to beat this n cube limit while still kind of working on this time to city representation. So we have limited resources needed, and these are the most simple quality measures we could work on. However, the question is, did we accidentally complicate the landscape of this optimization function, in the sense that this new Hamiltonian will be too complicated to optimize this ansatz? So we made some numerics. Unfortunately, TSP requirement grows very fast, so we're limited in the number of cities we could consider. And we cannot promise that our method will be the best of all the ones we consider. However, what we can say is that our method is not worse than it's at least comparable to all the other methods we consider. You could, for example, look at this dashed red line. We haven't considered integer linear program because it's actually much larger than the other presented here, but we expect it to be very bad, similar to the QWorld, which already for 4 cities gave very bad results. But there's actually one QAOA variant which was clearly better, and this one was GM-QAOA. The reason why I didn't plot this is not because we had issues with simulating this, but it was because GM-QAOA was so better that when I would plot this, then all the other plots will be basically squashed. The GM-QAOA was so much better. But the problem is that it comes with a price. GM-QAOA requires n squared qubits compared to n log n, which is for n case. It requires n squared depth. Perhaps this could be improved, but this is problem of having good unitary matrix which good unitary matrix which create a superposition of permutation. This is a problem which is considered for I think 10 or 20 years, and no one has came out about this. And our has n log n depth. Also, as before, we have n squared gates versus n to the cube gates, so there's also some extra improvement. So GM-QAOA is better in number of levels, but it will likely be worse for niche devices in terms of other factors. Now, let me just finalize this with one more slide about generalization. As Ben Chebako mentioned in the previous presentation, we actually consider this for set cover problem, also for integer linear problem, graph isomorphism problem. The thing is that actually, as expected, we cannot promise that the depth, gates, and number of qubits can be simultaneously reduced to the bound values of the bound. Actually, at this moment, I would say that the graph isomorphism, its general version, we only have to between number of qubits and number of gates and the depth of the circuit. So, in particular, this graph isomorphism problem is, I would say, the big open question whether it could be drawn. It could be taken below this current trade-off and say close to the optimal values, or whether this is a particular example where we reach this, where it reached this suboptimal limit, which is also very possible. Thank you very much for listening to my presentation. And if you are interested, I'll be happy to answer your questions. I'll be here on Discord.
Thanks a lot, Adam. It was super nice presentation, and also like really, I think even pedagogic, like in the sense that I think everybody got like these nice results, like what they mean. So actually, there was a question for both you and Akash. Sorry, Akash asked a question from both you and Benza. This is what I wanted to say. So he likes a lot this algorithm, and could you please comment on how the Qiskit simulators handle pointing towards the composition, the multi-control top-volley while simulating, and how the 1 and 2 qubit gate number increases?
So this very strongly depends on the number of ancilla qubits you have. If you have no ancilla, then basically you need at this moment O(n) squared. The problem is that this particular decomposition is not implemented in Qiskit. There was some variant, efficient number of gates without ancilla, but it turned out that this paper was wrong. They had some local phases issues. And thanks to the bench's work, we were working on the efficient implementation, which, however, is actually not published and not implemented in Qiskit. However, I would say that overall, our implementation would be better if we could spend a little bit more qubits, and we use implementation of top-volley with ancilla. And in this case, I think the number of qubits can be reduced to O of n. So it will be proportional to number of controls. And this is something which is well implemented in Qiskit. It even includes the aspects that some top-volleys can be replaced with the relative phase top-volleys, so that it acts correctly in a bit, but simply adds some phases.
Sorry, I was muted. Thank you very much, Adam. This was like a really proper explanation. So I think basically our time is finished, but I think there is a lot of things to be discussed about this algorithm and also the other algorithms that were presented. So I would say we end the session now. Thank you very much.